true honor to be here and to speak to you today. I also really like to thank the organizing committee of the conference. Thank you so much for inviting me and for your warm hospitality. So I work with robots and flying robots in particular. And we work on writing the algorithms that enable those drones to do tasks on their own. And I'm particularly interested in how we can use robots to empower us. And to be a bit more explicit what that could mean, let's look at this video. So this is a flying drone. It has a camera, it is on a leash, but it can provide videos and photos that we could not get in any other way. So who of you has taken a video or photo with a drone before? Anyone? So it's really an experience, because only then you really understand what kind of potential this technology has. It really can place your camera, instead of just in your hands, anywhere in the 3D space. But you know, drone technology is not the only technology that extends our abilities, and philosophers and filmmakers have long seen technology as being an extension of our human body. And let's look at these examples to really understand what that could mean. I mean, without technology, we couldn't explore undersea worlds. Without technology, we couldn't fly. So it provides us the ability to fly. Without technology, we cannot communicate with other people somewhere completely on a different side of the world. And technology is even used in art to, you know, extend our way of expressing ourselves. And drones are not an exception. Drones also extend the abilities that we have as humans. And today, if we look at what flying drones can do, they are either used as a sensor in the sky, similar to what I showed you in the video before. And so they may be used to quickly assess a disaster scenario, or they are used in agriculture to assess the growth of the crops, or to assess the health of power lines. The other big application area of drones is transportation, using them as a transportation device. And you may have heard of Amazon or other, I'm sure there are also Asian companies that propose to deliver packages with drones. But you could also think of delivering a defibrillator to a person who is suffering a heart attack. And most recently, it has been in the news a lot, using drones to transport people. So having a drone without a pilot to fly you to any destination. So these two core application areas show how drones could expand our abilities. So what I want to do in this talk is to give my personal history about how I came to work with drones, and how drone technology has developed over the past 10 years. So I started my PhD 2008, so that's exactly 10 years ago, at ETH Zurich in Switzerland. And after that, so in 2013, I then became an assistant professor at the University of Toronto in Canada. And I want to kind of highlight how during this time drone technology has developed. But very briefly, so the University of Toronto is located here, just at the border to the United States. It's a large school. We have 85,000 students. It was founded in 1827 and is usually ranked #1 in Canada and among the top 20 universities worldwide. But importantly for this talk, it covers a broad range of disciplines, so you can study everything from law to business to medicine and engineering. And it's really interesting to talk to the colleagues about how robotic technology can be used in those different disciplines. And anything that you see today is due to an amazing team of people, so that's my current team of students. And you see some of the flying vehicles we work with. So in my talk, given that this is a consumer electronics conference, I want to do two things. I want to show what we do in research, but also how it connected to consumer electronics that you can buy in stores. So I will show and go over three main areas we have done research in and we worked on. But then I want to connect it to how this it was intertwined with how consumer electronics developed. So to get started, when at the start of my PhD, that was around the time when the first Apple iPhone came out. So 2007, the first Apple iPhone came out. But even before then, 2006, DJI, which is the biggest drone manufacturer in the world, located in China, and has currently a market share of 70%. This company was already founded, but what they sold were DIY drones, so do-it-yourself drones, mostly for really, really excited hobbyists. So this was kind of what they sold. They sold these single components, and then real technology enthusiasts could come and build their own drone and fly it with a remote control. So that was roughly the time when I started my PhD. And the first drone we worked with looked like this. And we also bought the different parts from a smallest German startup and started working with it. And so if you get such a drone and you want to fly it manually, how you usually do it is you observe the drone with your eyes. You kind of process this information, and then you send commands to the drone through the remote control. And the typical commands in this case are called roll, pitch, yaw, so the rotation around the 3 axes of the drone, and then thrust, which means how much all propellers work together, like how much force they produce together. To fly a drone, I'm not sure if anyone has flown such a relatively standard drone, it takes a lot of practice. It took me a lot of practice to just keep it in the air for 10 minutes. So as you practice as a human, you learn better and better how this vehicle behaves and how you need to move the sticks to keep this vehicle in the air. And it's really not easy. I mean, if you're an expert game player, you may learn it faster than I did, but it's not an easy task. So what we try to do in our research is to do that with a computer. And the loop looks very similar. So you have the drone here, and then instead of my own eyes, we have cameras at the ceiling that observe the vehicle and tell us exactly where it is. It's like a very precise indoor GPS. And this information is relayed to a computer, and the computer now needs to do what I was doing before, and needs to send commands to the vehicle through a wireless link. So I told you that it needs a lot of practice to understand how the vehicle behaves and then how you can control it. If we want the computer to do that, we have to somehow teach the computer to do that. And usually how we do this is by describing the vehicle behavior with mathematical equations. So we come up with these mathematical equations that then we can turn into a computer program that can actually fly this drone. And then this looks like this. So here the drone should stay at the position where it is. And even if I really push it really far away, it really nicely and elegantly comes back to the position it should be at. So this is called feedback control. It's a type of mathematics that describes moving objects. And so we designed this controller based on our physics understanding of the system. And in the video I showed you, we said the vehicle should just stay at a certain fixed position, and then we try that the actual vehicle behavior is as close to the reference signal as possible. And this loop allows us to do that. So when we started our research, what we really only wanted to do is really push the boundaries of what drones are able to do, without kind of having a very specific application in mind at all. And we know that feedback control can enable behavior that would not be possible otherwise. And to convince you that this is true, you can look at this video. So here we fly 5 vehicles, and they switch positions and do so without colliding, and they all arrive at the same time at the new target location. And that would be impossible to do with manual control, right? You would need 5 pilots somehow coordinating their behavior. So this kind of feedback control can be very powerful to achieve behavior that we couldn't do otherwise. So this started this first theme of research where we just wanted to enable drones to fly on their own and achieve really agile multi-vehicle flight. And so we were the first to aim for fast, agile multi-vehicle flight. And how we wanted to demonstrate that is to enable drones to actually fly to music, like dance to music. Why did we choose that? Just because, on the one hand, it was really fun, and on the other hand, it requires really high accuracy in terms of being in time, being in the rhythm of the music, and performing accurate motions. And so what we do is you could come with your favorite music. We analyze it offline with a computer program. Then here a user can pick motion primitives, motion samples, and concatenate them. And then we need a vehicle controller, as I showed you, to kind of execute those motions. And there were 2 key parts. On the one hand, we needed this collision-free transition to transition between different motion primitives. And so we developed an algorithm for that where we solve an optimization problem. So if we want to go from this configuration to this configuration, the computer algorithm would compute the path for each of the vehicles to avoid collisions. And then we needed very accurate motion music synchronization because that's usually how the behavior looks like for faster motions. If you want the vehicle to do the red line over time, so it's kind of a side-to-side motion, you want to do that, then what the vehicle actually does is not perfectly aligned. So usually it's a little bit delayed, and also the amplitude is different. So by looking at those plots, we could see those offsets and then compensate for them. And so here is how we slowly progressed in achieving this goal of having dance performances with multiple drones. So in 2009, this was kind of our very first motion, only side to side, and trying to be in the rhythm of the music. Then 1 year later, we had 3 vehicles and already a bit more interesting motions. And then another year later, actually didn't end here. Later, Cirque du Soleil became interested in this technology, and we did the first pilot project. So here, this is an actor, and the lampshades are our flying vehicles. And if you think the vehicles react to the actor, it's the other way around. So the vehicles are pre-programmed and the actor is just really good at acting. And so this became eventually a show on Broadway in New York for 1 year. But we started here, we kind of did, between 2009 and 11, those first performance that I showed you. But in the meantime, on the consumer electronics side, Parrot, a French company, came out with the first drone that could be flown by non-experts. So this drone could fully stabilize itself without you doing anything. So it could stay in the air on its own. It used an ultrasonic sensor for height and a camera looking down and optical flow to stabilize itself. So this was the first drone that could actually be very easily flown by everyone. And so they presented this in 2010, and then in 2011 at the Consumer Electronics Show, they started doing these kind of dance performances to promote their products, and they got better at these dance performances over the next years. But even more interesting, this became a real industry. So today there are, more than at least those four, but many more companies that do drone performances on stages at concerts, on stages, on cruise ships, outside. Intel works together with Disney to do outside shows. So there is a huge number of companies that now use drones for performances. And the latest, biggest one by Ehang was flying 1,000 drones at once. So it has really become kind of an entertainment business. What we looked at next was further pushing how these vehicles can fly. And to do that, we use machine learning. So our motivation was to do really high-speed aerobatic maneuvers. And for those maneuvers, our standard approach that I showed you before with feedback control would not work anymore. Because at those high speeds, our mathematical models of how this system performs were not accurate anymore. So we needed to do something else. And what we did is we basically just collect all the data there is if the vehicle flies, and use it to learn updates for our controller and input. And really what it does is, by combining this control with learning, we can make these robots even smarter. They are not anymore limited by our understanding of their physics, but we can use data to complement that. And so the first task that we tried to do was a triple flip, which means a vehicle starts here, should do 3 times 360 degrees of rotation, and then come back to its original position. And if we just used our physics knowledge of how these vehicles behave, that's what was the best that we could achieve. So it would start doing this triple flip, but then it flies off. It wouldn't get better because there's no learning. But once we enable learning, then it starts being still quite bad, of course, but then over time, we gather data and we can learn from that data to improve the performance. So now you see at least it ends, you see it's getting better, it's getting closer to stopping where it started, and now it's already pretty good. So what we did there was we had 5 parameters, and over the learning iterations, we would adapt them. And so you see how they were adapted, and quite significantly over time, to make this task possible. And so here on the right, you see the model is what our physics model would think the vehicle can do. And then you see iteration 1, which is very much off. So there is a model mismatch, some aerodynamic effects that we don't understand. And eventually we can do the task, but it doesn't look exactly like the model because of this model mismatch. So we can do the task, but you see there's a difference between what our model thinks a vehicle does and what it actually does. And so we did another experiment where we wanted to fly as quickly as possible a slalom with these vehicles. And again, if we don't use learning, this was kind of the performance that we got. And our physics model would tell us that this should work, but somehow we missed something. But we can learn, so we can practice with these vehicles above the poles. And so they can observe their own mistakes and then correct for them. Similar to what you as human do. If you play an musical instrument, you practice a lot and you notice your own mistakes and then you correct for them. Or if you play a sport, some sports. So only after 3 practice runs, it can eventually do this task and fly through the poles. But you see it's at a very high speed and especially high angle, which is something where we know that our mathematics models are not good enough. And so here's a learned result of another configuration. And here is the one that it failed before. And this is all real time, no speed of the video. So that was about the time when I finished my PhD. And interestingly enough, Parrot, the French company, actually implemented the flip, not a triple flip, but a single flip, in their second version of their flying AR drone. But at that time, when I finished my PhD, that's also when DJI, founded already in 2006, came out with their first consumer drone. And since then, consumer drones have developed at an amazing speed. And these are just a few of the most recent platforms. One down here from Skydio can actually detect obstacles in the space and take videos from you while still avoiding obstacles like trees and buildings. This is a developer platform from DJI that we use in our research, but all of those drones get smarter and smarter. So they start to detect obstacles in the space and avoid them. And this very, very fast development recently, and almost every week there's a new drone product on the market, is largely due to the smartphone market, because really smartphones have driven the industry to develop small, inexpensive, and very powerful sensors and computing. And if you look, if any of your smartphones, it has all the sensors that a drone needs to fly on its own. It has usually cameras, accelerometers, gyroscopes, a GPS sensor, even temperature sensor and pressure sensors. So basically, a drone is nothing else than a flying smartphone. If you take your smartphone and you attach 4 motors to it, it would have everything it needs to fly. And so that has helped a lot to quickly develop this technology and make it affordable. So after I finished my PhD and moved to Toronto, I continued working on machine learning algorithms for drones, but I also looked more and more into drone applications, so using drones in industries. And for both, there was the inverse effect. It really helped us that the consumer electronics market was developing so quickly, and we could use those platforms for our research, because developing hardware is very slow and expensive, so using some of these platforms is extremely helpful. So our current goals in our research are twofold. On one hand, we want to make drones more and more autonomous, and on the other hand, we want to industrial applications. And here you see two applications we work on, for example, using drones in mining or to monitor large industrial sites. So both of these in common that we try to build drones that require minimal human input and empower non-experts, like anyone here in the room, to use those drones. Because in those application areas, there are not necessarily people that know how to fly. But to make this happen, you really need an interdisciplinary team of people. So we have a Center for Aerial Robotics Research and Education at the University of Toronto, which brings together researchers from all different fields, including people who design new materials and people who work mostly on computer vision, as well as people who are experts in aerodynamics. And actually, something which might be interesting to you, we also do a lot of outreach. And so, for example, one outreach event we have is a youth drone racing competition, which is a Chinese Canadian initiative. But we also, I'm also affiliated with the Vector Institute, which is a center for artificial intelligence, and with the Institute in Mining, where by working in this application area, you really need experts to understand this. So let's have a look. So what are the challenges that we try to address? One big challenge is still that all robots, not only drones, need a lot of manual programming and tuning to make them work. Yeah, every industrial robot that you see, all these robots that build our cars, each robot is programmed by a human to do exactly the task that they should do. So we work on algorithms that do this more automatically, such that we as humans can only provide very high-level instructions and then the robot figures out how to do it. Then what is also still challenging for all robots is to deal with unknown effects in the environment. For example, for flying drones, dealing with wind or bad weather in general. And so I want to show you one result where we use deep neural networks to improve overall performance. And then flying vehicles are heavily dependent on GPS, but we also know that we can easily jam GPS, and GPS is not always available everywhere. So to have safe operation, we need some alternative to GPS if GPS fails. And so I will show you how we can use computer vision and cameras on drones to do that. So let's look at the first one. So for the first one, we want a drone to figure out itself how to fly. And so how we do this is only by flying it 10 seconds manually. So I take this drone and fly it 10 seconds, and then from that data, we have an algorithm that computes itself a controller and also tells us how safe it is. And so after only taking 10 seconds of data, this is kind of how the vehicle flies. It's not great, it wobbles around, but at least it stays in the air. But as it flies, it can gather more information, right? It can gather more data and learn to improve its own flying performance. And so with a total of 40 seconds of data, the vehicle figured out how to fly itself. So this is only a first step in the direction of enabling robots to figure out themselves the low-level controls, and we as humans only have to give them very high-level instructions. The next one is a fun one, where we kind of, you saw this standard loop before, so now we put one block here in front, which we learn, which is a block that that kind of tries to compensate for anything that our model may have missed. And so how we test it is, we allow, if you come to our lab, you can draw a motion on a tablet, and then the quadrotor will fly it. And if you use a standard controller, you know, it's not perfect. You saw the green line and the red line don't perfectly match. And now you see it's much better if we use this enhancement through learning. And so here it was a 56% improvement. And then we invited people in the lab to get very different random trajectories that the vehicle should follow. And so they all gave us some drawings. And then we tested our learning method. And here you see the result of the learning. And usually it follows the motion quite well. So we continue working on this, but definitely you can do a lot by using more data. And if you come to the lab, this is ready to try out. So if you should you ever come to Toronto, let me know. We did much more learning. So what I showed you here was how we can learn a model. I showed you before how a robot can learn through repetition. But we also have more recent results how different robots can learn from each other, or how we can learn safely. Especially for flying vehicles, it's particularly important if a vehicle starts to learn and it makes a mistake and then it crashes and falls out of the sky. That's not something that we'd like to see. But the last result I want to show you is how we work on improving or getting rid of this dependency on GPS. And the dependency of GPS is problematic for two reasons. If we, as with my research, if we want to fly, we have to explain the authorities in Canada how our flight experiments are safe. And to explain how they are safe if GPS fails, usually the only option we can tell them we have a human pilot that can take over, because that's the only alternative that we can have. But that limits us, because that means there must be always a human pilot, and the human pilot must be so close to the drone that it can see it and take over. So to enable flights that are far away from a human pilot, we need some alternative to GPS. And the other reason is, if we are flying in downtown Toronto or anywhere where you have large high-rise buildings, GPS is not great anyway. So we need something as an alternative there. And so we just came back 2 weeks ago from experiments in the northwest of Canada. And there we flew this vehicle, which is actually a DJI developer platform, at about 50 kilometers per hour. And it doesn't use GPS, it only uses computer vision. So what it does, it first flies over this area and records lots of images, and then it tries to localize against it later. So it's a little bit similar to when you go to a new city and you navigate the city without a map. Then you try to remember key locations, like you turned left and you remember, oh, there on the right there was this coffee shop and on the left there was this. So that's similar to what the drone does. It flies and it tries to remember those key locations, and then if it sees those again, then it knows where it is. And so here's a little video replay. So that's basically what the vehicle sees here on the top right. That compares its current point of view with what it has seen before, and the lines represent the offset. So it represents where it is with respect to what it has seen before. So it can fly with up to 50 kilometers per hour, maybe even more. We didn't try faster, and localized relatively reliably. So that was in terms of how do we make them more autonomous and safe. But how can we make them more useful? So we look at these 4 application areas, mostly because there's some interest in Canada for those areas. So one is construction. So how can robots, flying robots, monitor the progress in construction and also see if the construction workers make any mistakes? And then how can they be used in mining to make the mining operation more efficient? And then in Canada, we have several nuclear power plants that get older and older, and they want to monitor the structural health of those buildings. And so here's just a little video from a flight in a mine in Mexico that we did. So the vehicle is up here, and these are my students. And so you really have to talk to the mining engineers to understand what information is useful to them. But here we study the rock at the rock faces. And with a drone, we can cover a much larger area. Usually a human is doing this and just taking 1 or 2 images. Now we can fly kilometers and take images. And we also don't put a human at risk because those walls are sometimes not stable. And so that we can produce this 3D image, but that's not that really important for the mining engineers. What is really important is to then interpret this information. So I'm not a mining expert, but they need to see the orientation of the rock walls, and then they are interested in these digital models to understand the rock structure and understand where they may find the most gold in that rock. So you really need to understand what information they need to help them out. But the drone can do a lot of useful measurements for them. And I stop here. So drone applications are really interesting, and I think also something that so far a lot has been driven in terms of drones by consumers, and the majority of our products are about taking pictures and videos from the air. But now there is an increased interest and focus on understanding the specific industrial applications and how drones can be helpful there. And I see it a little bit like the computing technology. I mean, computers basically have changed jobs everywhere, in every industry. And so robotics, I believe, will in the future also change jobs in every industry. So overall, what I wanted to show you is that there's a lot of interaction between what research has been doing and then also how the electronics themselves influence, again, what we are able to research on at the university. And these cycles are extremely fast if you think about it. Like, I mean, 2009 we did these multi-flips, but then 3 years later you could buy, everyone in the world could buy a product that has something similar. Or on the other hand, with all the consumer drones that came out, we could immediately do better research. So this interaction is getting more and more interesting and agile. So what I want to end up with is looking at where are the future opportunities and challenges. So if you look at the opportunities, I think a big opportunity is still, and I showed you some examples, how we can combine artificial intelligence and machine learning with robotics. Robotics has the feature of being a physical device that can actually physically interact with the world. And so if we make it smarter, then this could be robots could be of tremendous help for us. And then overall, robotics and the drone technology, on the one hand, creates new industries, like, for example, drone performances that I showed you, but they also disrupt all the old industries, like transportation or mining. what are the challenges that we all need you to work on? I showed you GPS dependency is still one of the biggest challenges. Flight time is a challenge because these drones usually don't fly longer than 30 minutes at a time. A big open question is how we manage the traffic in the air. So right now, it's if I want to fly with my team for a research project, at least 24 hours beforehand, I need to tell our authorities that I want to fly in a certain area, and then they reserve that airspace for me, and nobody else can go in. And so, but imagine there are lots of drone operators and maybe flying car manufacturers and others, and they all want to fly. So there's much more density. So we need some more flexible approach to that. Because ideally I would, in the morning, reserve the flight space, fly for 10 minutes, maybe 30 minutes, and after I'm done, I release the airspace for anyone else who wants to fly. Then another open question is how we do this safe beyond line of sight flight. So meaning a drone that flies further away than what an operator can see. And for that, it needs to understand its situation well. So it needs to understand where there are obstacles, if there is a power line in the way, and it needs to detect that and avoid that. And those information is usually not captured in maps, so it really needs to detect this. And this is similar to what self-driving cars need to do. A self-driving car needs to understand the surrounding, needs to detect the other cars, passengers, and so on, and react to it. But for flying drones, it's much more challenging because you cannot carry heavy computing. And you need to make decisions much faster than cars have to because your dynamics are so fast. So it's a similar problem as self-driving, but in some way more challenging because everything you need to take into the air. We need to, of course, look at how we can make the performance of flying vehicles reliable in any weather condition, in any wind condition. And I think something that's really not explored a lot yet is this interaction between the robot and its environment and the humans. I mean, ultimately, we are physical. We can interact with our environment. I can move things around. Robots can do that. But the interaction of the robots is usually held to a minimum because it's difficult. But I mean, that's the biggest potential of robots. And finally, we need to educate people in these fields. And so, as was mentioned in the introduction, right now I'm with a team of people. I'm teaching this online course on flying cars and autonomous flight. And right now there are 800 students enrolled. But there's a lot of knowledge that you need to make robots work. You need to understand the hardware, the software, and everything, but it's really, it's a skill that is very much in demand right now. So to conclude, I want to give you this picture, which kind of is a futuristic drawing, but also shows that we have to think about how we want to use the technology in the future. And there's a really good quote, which I'd like to cite, is that the most exciting breakthroughs of the 21st century will not occur because of technology, but because of an expanding concept of what it means to be human. So if I interpret this for myself, what I think we could learn from this is that whatever technology we develop, it will be the most successful if it expands our abilities in a way that we find engaging and helpful. And so before even thinking about exactly how the technology must be developed, we should probably think about what we want the technology to be and then help us develop it. everything I showed you was, of course, a team effort. So you see my team. There's also students working on self-driving, but I didn't want to talk about that today. And I had amazing collaborators both in Toronto, but also at ETH Zurich. And I'm happy to answer any questions. Thanks.
Currently, external drones are legally limited to within a few kilometers of the airport radius. Later, when those became common, is there a solution to this problem by any chance? Because you said that set the time to fly on drone, but near the airport there are always many plane.
Okay, so I'll try. Let's see if I understood your question. Otherwise, you can ask me again. So, yeah, so close to the airport right now, you cannot fly. Just because close to the airports, the airplanes are low, right? They are landing or taking off. And so that's the main reason. So they are low enough that your drone can interfere with the airplanes, right? This may be relaxed as well once I guess the authorities have better figured out how to make the airspace more flexible. Right now, there's a person watching the airspace on a big screen, right, at the airport, and it sees those dots, and if it sees two airplanes come too close together, then a person makes the decision to say one plane needs to go down and one goes up. So that's okay if there's only a few planes in the air, but if we have lots of vehicles in the air, that's impossible to do by just a single person. Was that your question? Yeah? Okay, thanks.
I have operated the drone myself, but I've learned new ways to operate it with algorithms. What's the difference between controlling a drone and using algorithms to navigate the path?
Okay, so you flew it manually did you fly it manually with a remote control?
Yes.
Yeah, so an algorithm does basically what you as a human did, right? So it constantly needs to know where the vehicle is, and then the commands that you send, the task that you did, that's what the computer then does. And if a computer does it, usually, it's more repeatable and more accurate because a human has some reaction time. So we are not super fast, right? We need to process the image and then do actions. So a computer can do the task more repeatably and reliably, and a computer doesn't get tired. So overall, I'm not sure how good you were at flying, but it's not a problem for a computer to fly a vehicle for many hours. It's challenging as a human to do.
Deep learning consists of the training and inference part. Also, in your deep neural net, and training is done solely by the drone or other servers. The training of data is done by the drone itself or by other computer systems.
Okay, yes, very good question. So how the deep learning worked was a drone would fly in the air, a set of motions, basically just explore faster and slower motions, and then we collect all the data, and then we do it off board. Yeah, so we collect all the data, a computer off board our PC on the desk is doing the training, and then we use the result on the drone.
Okay, I
It's not
understand.
on board. It would be nice if it would be, but right now.
Can I have a question? Yeah. Thank you. It was very impressive to listen to your lecture. I'm a teacher from Jeju Science High School. I'm my major is not the science area. I'm an English teacher. My second major is geography. And then I have a question. Like, you mentioned about some applications about like some kind of drones and some that kind of kind of advanced like technologies like construction or mining or that kind of things. So do you have any plan for developing this kind of technology for the disaster relief for the future? Like, because we have a lot of problems, we faced a lot of problems of disaster nowadays. And second, it was kind of, you mentioned about developing this kind of modern technologies to expand our human ability. So it means like I understand it's kind of using, expand our like human body ability into the technology and using the environment. But do you have any plan to protect environment problems with this kind of modern technology? Modern technology. So as a kind of non-major scientist, I want to know what kind of plan in the future, not just construction or mining or the kind of transportation area, just about like protecting environment or disaster relief, that kind of areas. Do you have any plan for that?
Mm-hmm. Okay, so the first part of your question, how if we have plans to use it for disaster relief. So right now, no concrete plans, but that's more, not that I think that, I do think it's a really important area. It's more that I don't have the collaborators or the interest right now to work on, like of other people to work on that. But I do think it's really powerful. And it has been shown in most of the recent disasters that people have been flying drones to quickly assess which areas were affected and to quickly help the people or guide the emergency personnel to the right areas where most of the people were injured. So I think it's really powerful. And you could even, you can fly with a normal camera, but you can also bring a thermal camera, so it detects temperature. And this way you can quickly detect where people are because we are warmer than our environment. So I think it's a really powerful technology for this. In terms of environment, that's a very good question. So how can we develop, if I understand you correctly, your question was, how can we develop technology that respects the environment and is sustainable? Yes, I think it needs to be addressed. In some way, I do think we have to push forward and see what technology can do, to then have the right regulations and rules in place by the government to protect our environment. Most of, for example, all the drones that I showed and the flying cars that people envision, they are driven by electric power. So how you get electricity then very much depends on each country. Like in Canada, we have a lot of electricity from hydro and from wind and hydro. So that's very environmentally friendly. And electric motors don't have any exhaust or pollution this way. But it depends. So I do think that it's something definitely to consider, right? In the development.
You mentioned a lot of auto flight system for drones, and I heard that LiDAR technology is very useful in self-driving cars and making maps and so on. So I'm curious about whether drones can use LiDAR technology for self-driving system.
Mm-hmm. Yeah, so this is a very good question. So he was asking if we could put another sensor on a drone, not a photo camera, but a LiDAR. A LiDAR basically takes a picture, but for each pixel it gives you a distance. So it's it's a very powerful sensor for self-driving. The same for self-flying, but I think often technology can be pioneered in self-driving and then eventually come to flying. So for flying right now, this big drone that we use for our field tests recently, we also have flown it with a LiDAR, and we have used the LiDAR on that. But right now, the LiDARs that we can carry in terms of the weight, they don't give us a very high resolution. So they are not, I mean, sometimes useful, but not that useful. And the processing of all that data on board is very expensive and requires a lot of computing power, which then requires, heavier computers on the drone, and this reduces the flight time. So I think eventually, yes, if LiDAR technology becomes smaller and lighter, but right now it's basically a physical limitation that it's too heavy right now.
Unlike a helicopter, the drones have 4 propellers. I want to know why many drones do not use 6 or 8 propellers. And I saw video that developed drones that kill people on YouTube. What do you think about killing people with drones?
Yeah, good questions. So the first question was about why do we have 4 propellers? So 4 propellers is the minimum, such that you can fly any 3-dimensional path at any speed. So you are completely free to fly anywhere at any speed, so you need those 4. But the 4 are not enough to control every, what we call, degree of freedom of the drone. So if a drone wants to fly forward, it needs to tilt, and then it can fly forward. So we cannot control the orientation of the vehicle. If you have just more propellers, but all in a plane, this property doesn't change. So then more propellers only help you to be safer in the sense that if one propeller fails, you can still fly relatively well. But there are flight concepts that look at expanding what a vehicle can do. So flight concepts where you can fly forward, but you don't have to tilt. You can just stay flat. So I do think that the design of these vehicles is also not matured. The 4 propellers is just the very simplest way. You just need a cross and 4 propellers, and that's all. So it's mechanically extremely simple. But people still explore different designs. The other question was around that this technology can be used to kill people. Yes. So initially, when we started our research, when we did this dancing vehicles, people had the consumer market was not there, and they would always compare our work with military applications, which it was not, and we never got money from the military or anything. But that was the only thing that they could relate to. I think now we see lots of commercial applications of drones, and people understand the value of this technology. But as with every technology, this technology can be misused. And this is true for any technology. And we have to kind of, with laws and regulations, make sure that it is used in the proper way. But of course, you can misuse this.
Okay, that was the last question. Let's thank the speaker again once more. We'll probably never see her again in Korea again. So, loud so that they may come back again.
Thank you.
Thank you so much.
Thank you.